In the previous lecture, we started the discussion on something called universal gates, which are nothing but the NAND gate and the NOR gate, which we claimed were called universal gates because apparently they could be used to implement any possible logic function. So let us now take up the task of proving the statement. That is, we can realize any logic function using only NAND gates or only NOR gates. So to do this, we need to know what we are up against. When we say that we can realize any logic function, we mean that any particular logic operation can be released or can be realized. So therefore, we know already that there are, so to speak, three basic logic operations which form the foundation for all possible logic functions. And those basic logic functions are nothing but AND, OR, and NOT. If I write them symbolically, it will be the dot, the plus, and the bar or the complement. So therefore, we can say that if we are able to realize each of these functions individually using only NAND gates or only NOR gates, we are done. That means we can realize any logic function using only NAND gates or only NOR gates because all logic functions have these three operations as their basis. So once we are able to realize each of these functions individually, we can realize any logic function under the sun. So therefore, let us try to do this. First, let us try to do not using NAND. Let's choose the NAND gate first. So what we want is we have a single input and a single output. Suppose we want the input is A, so therefore the output Y should be A bar. This is what not function is. But we have to realize this using NAND gates. Now how do we do this? We can do this by putting a NAND gate in this format. But as we know, even though we have one input, a NAND gate needs minimum of two inputs. So therefore what we can do is that since there is no possibility to give any different input in this case, this A will go to both the inputs of this NAND gate. So therefore this is A, this is also A. Therefore, the output will be A dot A the whole bar. So if you are ANDing a quantity with itself, you get that quantity. So therefore, Y is nothing but A bar because A dot A is A. You can prove this very easily. So if 0 and 0, the AND becomes 0. 0 and 1, the AND becomes 0. One and 0, the AND again becomes 0. 1 and 1, the AND becomes 1. Right? So therefore, since we are talking of a dot a, we can actually do away with the second and third cases because a and a always have to be equal. So therefore, what we are saying is that if you're looking at this and this, the first and the last row, you see that the outputs column also corresponds to a. So therefore, this column a dot a is nothing but a itself. So therefore, using a single NAND gate, we have realized a NOR gate. Now, let us try to realize an AND gate using NAND gate or NAND gates. So here, now we need to have two inputs, A and B. And let's suppose we want the output Y should be the AND of A and B. So therefore, the simplest thing to do intuitively is to put a NAND gate over here. So therefore, the output at this point will be the NAND of these two, that is A dot B, the whole bar. Now what do we want at the output? We want that the output should resemble an AND function, that is Y equals A dot B. Here I have A dot B and here I have A dot B, the whole bar. So what we need is a complementing operation. What we need is a complementing operation. And what is that? The gate that does a complementary operation is nothing but a NOT gate. But now we want to use only NAND gates. So therefore, what we need over here between this point and this point is a NOT gate. And the NOT gate should be made using NAND gates, but we already know how to do that. So therefore, this thing we will put over here. And there we go. The same principle applies. This is a NOT using NAND and this is just a NAND in the normal way. So therefore, using two NAND gates, we are able to realize an AND gate. Next, let us try to realize an OR function using NAND gates. So to realize OR using NAND, once again, we will have two inputs and we need the output Y that should be equal to A plus B. This is what we need. Now, we are in a bit of a dilemma because we have this plus thing. And whenever we are using NAND, we have a dot. So therefore, is there any way with which we can try and convert this plus into a dot? Can we convert this plus into a dot? Well, one way to get started is to rewrite this expression slightly differently. I can say that any logic variable is nothing but the complement of its own complement. For example, if I have a number x, the negative of its negative would be equal to the original quantity. So therefore, I can say if I treat the negation as a complementing operator, I can say that this is nothing but a plus b whole bar. This is what I can say. Now, what I can do is I can keep the outside bar as it is, and the inside bar I can look at it more closely. The inside bar I can look at it more closely. Now, consider this quantity a plus b, the whole bar. Even after putting these two bars on a plus b, we are unsure how to proceed because this plus sign seemingly is always there. This plus sign seemingly is always there. Now, to help us out, there was a mathematician many years back who helped us or who helped understand this expression a little better. Now, suppose I write a truth table. This a plus b, the whole bar, is nothing but a NOR operation. So, we already know what the NOR looks like. A NOR is just opposite of OR. Here it's 1 and the rest are zeros. That mathematician many years back said that this function can also be represented in a different way. He said rather than taking the complement of this thing, you take the complement of the individual variables. That is, you write a bar and b bar. Okay, so a bar would be the opposite of a, that is 1, 1, 0, 0. And b bar would be the opposite of b, which is 1, 0, 1, 0. And he said, you take these two and that is, you do a bar dot b bar. So if you are adding these two, you get 1, 0, 0, 0. What do you observe? You observe that these two are exactly the same. So therefore, this quantity a plus b, the whole bar, can be written as a bar dot b bar. So therefore, if I now resubstitute this over here, what this will be? The outside bar will still stay, while the inside bar will become a bar dot b bar. Now, if you look at this, it is a bar dot b bar, the whole bar, which is like saying, it is almost like I have a NAND gate that is combining a bar and b bar, because that is why the output is a bar dot b bar, the whole bar. So therefore, immediately what I can do, I can place a NAND gate over here, whose inputs should be a bar and b bar, just like this. So we have a over here, we have a bar over here, we have b over here, and we have b bar over here. So that should not be a surprise anymore. We know how to convert a to a bar and b to b bar using NAND gates. That is, we will use NAND to realize a complement. This is how you can realize an OR gate using a NAND gate. Now, the mathematician who came up with this relationship where a plus b, the whole bar, is equal to a bar dot b bar, his name was Augustus De Morgan. But even before De Morgan came into the picture, there came a mathematician who actually studied logic functions in a lot of detail. He said that if you use logic functions or logic variables which can take two values, that is 0 and 1, or yes and no, or true and false, whatever it is, a very interesting set of algebraic relationships can be established, which in some sense would be very similar to the algebraic properties we know today for decimal numbers, and in some sense they would be different also. So the mathematics behind using these kind of variables which can take two values, 0 or 1, this mathematics was studied in detail by a British physicist whose name was George Boole. And the set of theorems and the mathematics he published, that is called as Boolean algebra. So Boolean algebra or Boolean operations, they can be done using variables which can take two values, as I mentioned, 0 or 1, true or false, yes and no, like that. So therefore, let us see some of the Boolean theorems. Which George Boole had proved. So he said a dot 0, that is, if you AND any Boolean variable with 0, what do you get? You get a 0. It's like saying if you multiply any number with 0, you get 0. And we know that is true because of the properties of the AND operation. If any of the conditions are not satisfied, the output is also 0. Likewise, a dot 1. It's like saying if you multiply something with 1, the answer is the variable itself. And it's true also. If you have a dot b and one of the condition is satisfied, you need to know what the other condition is. And whatever is the other condition, that is the output. The complement of a complement is the original quantity. Likewise, he said a plus 0. If you OR something with 0, you get the original variable. But if you OR something with a 1, if one condition is satisfied, it does not matter what the other is, the answer will be 1. Likewise, if you have a dot a bar, what will be the answer? If you have a dot a bar, if a is 1, a bar will be 0. If a is 0, a bar will be 1. Point is that whatever is the value of a, one of these two operators will always be 0. So therefore, the answer will be 0 because it's an AND operation. If you have a plus a bar, again, one of the quantities is definitely bound to be 1. So therefore, if any of the inputs is 1, the output will also be 1. So these are some of the very basic Boolean theorems which George Boole essentially theorized. Now, very briefly, we had discussed what Augustus De Morgan had done. So, De Morgan had proved essentially two theorems. He had essentially listed two theorems which are converses of each other. He said that the complement of a plus operation is equal to the dot of individual complements. That is, the complement of a plus operation is equal to the dot of individual complements. This is theorem number 1. Theorem number 2 is the complement of a dot operation is equal to the plus of individual complements. These are essentially converses of each other. These are called as De Morgan's theorems. We already proved this using a truth table. You can also prove the second one very easily using the truth table method, which we just saw a few minutes back, like this. You can prove this quite easily. Now, these are some of the basic Boolean theorems and De Morgan's theorems which form the basis of Boolean algebra. There are some other properties also. Let us take a look at them. Other properties of Boolean expressions. The first property is called the commutative property. Which says that A dot B is equal to B dot A. Likewise, A plus B equals B plus A. Once again, this plus is for the OR operation, not addition. So, whichever way you do this operation, the dot or the plus, whichever order, it does not matter. The second is called the associative property. That is, A dot in bracket B dot C is equal to A dot B in the bracket dot C. Likewise, A plus bracket B plus C would be equal to A plus B in the bracket plus C outside. Third is the distributive property. That is, if you combine the plus and the dot together, that is A dot B plus C. If you expand it, it will be A dot B plus A dot C. So far what we notice is that this is just like our regular algebra. However, the distributive property has another interesting, powerful feature. That is A plus B dot C, that will be equal to A plus B times A plus C. Now this is something very, very interesting. This does not happen with our normal, well-known algebraic quantities. Well, why? Because in Boolean algebra, there is nothing called square. If you treat A, B and C as normal decimal algebraic variables, and if you start opening the brackets, the first term that you would get would be an A square. And the concept of square in Boolean algebra is quite nonsensical. So, even then, we need to ask ourselves how this can happen. Well, let's prove. Let's prove this. Let's prove that this is indeed equal to this. We can prove it using truth tables. But then something tells me that so many quantities, the truth tables would become too big with too many columns. So therefore, let us start with the right hand side. The right hand side is a plus b dot a plus c, which if you expand would become a dot a plus b dot a plus a dot c plus b dot c. Now, what is a dot a? If you are ANDing a quantity with itself, you get the same quantity. So this becomes a. This one, using commutative property, I can again write as a dot b. Then I have a dot c. Then I have b dot c. Now what I can do is I can take a common in the first three terms, which is a in bracket. I can say 1, because a is nothing but a dot 1. 1 plus b plus c plus b dot c. Now b plus c, whatever it may be, we have a 1 over here. And as per the Boolean property, we know that 1 plus anything or 1 or with anything is always 1. So therefore, this is nothing but a dot 1 plus b dot c. And a dot 1 is a. So this is nothing but a plus b dot c, which is our LHS. So therefore, we can prove it like this also. So far, we have seen some of the basic principles of Boolean algebra. We saw what are the De Morgan's theorems. Just to quickly repeat, De Morgan's theorem is there in two parts. He said that the complement of a plus operation would be the dot of individual complements, and its converse, the complement of a dot operation would be the plus of individual complements. Thereafter, we saw some properties of Boolean expressions, that is the commutative property, the associative property, and the distributive property, where the second clause of the distributive property is very, very distinct and unique and is specific to Boolean expressions only, whereas all the other examples for commutative and associative can be applied to Boolean expressions as well as our normal decimal algebra. Now, when we spoke of De Morgan's theorems, we stated that the complement of a plus operation is equal to the dot of individual complements and the complement of a dot operation is equal to the plus of individual complements. So therefore, they are also called as duals of each other. These are duals of each other. If you take a Boolean equation, not an expression, if you take a Boolean equation, replace all the pluses with dots and the dots with pluses, and you also replace the ones with zeros and the zeros with ones, the equation will still be true. That is called as the principle of duality. So if you have a Boolean equation, Just to repeat, if you have a Boolean equation, you replace all the plus signs with a dot sign and the dot signs with a plus sign on both sides. And on both sides, you replace the ones with zeros and the zeros with ones. The resulting expression would still, or the resulting equation would still be a correct and valid equation. So, and if an equation is true, its dual is also true. So the dual of an equation refers to its form wherein all the pluses are replaced with dots, the dots are replaced with pluses, the ones are replaced with zeros, and zeros are replaced with ones. Right? So with this we have learned some of the basic working principles of the Boolean algebra, which we are going to use extensively in this course. So far we have seen some basic logic gates, and, or, and not. We have seen two universal gates, NAND gate and NOR gate. We saw that how using the NAND gates you can realize each of the basic functions, the basic logic functions. Thereby it proves that it is a universal gate. Similarly, just the way we realized each of the basic logic operations, the AND, the OR and the NOT using the NAND gates, you can do the similar exercise using NOR gates also. That I leave to you as an exercise, where you can prove and convince yourselves that indeed NOR gate can also do the same task. So therefore NAND and NOR are both universal gates. Interestingly, NAND and NOR are also in some sense duals of each other, because the dot is replaced with a plus and vice versa. So this is essentially a NOR operation and this is essentially a NAND operation. So therefore they are duals of each other. Now there exist two more gates which are neither basic nor universal, but they have some interesting properties. So therefore let us take a look at them. One of those gates is called as an XOR gate. The other is called as an XNOR gate. The XOR stands for exclusive OR. And XNOR stands for exclusive NOR. So the difference now is this. The XOR gate is very similar to an OR gate in the sense that for the first three cases it is exactly like an OR gate, but for the last case the output is a 0. And the XNOR gate is similar to a NOR in the sense that the outputs for the first three cases is exactly like that of a NOR gate, but the last one is a 1. So XOR and XNOR are also complements of each other. So the way to indicate XOR and XNOR gates are this. Again, they require a minimum of 2 inputs. So the XOR looks like an OR but with one more arc. And the XNOR is just like the XOR, but since it's the complement of XOR, there is a bubble over here. So one of the ways to write this is y equals a plus with a circle b. And here it is y equals a dot with a circle b, which is also the complement of the XOR operation. A XOR b, the whole bar. So you may now question what do these symbols mean? Do not get boggled down by these symbols. As I mentioned, XOR is neither universal gate nor is it a basic gate. So therefore, it depends on the basic logic functions. So in terms of the basic logic and or and not functions, the XOR gate is essentially this A bar dot B plus A dot B bar. Whereas the XNOR gate, you can find out the expression just by putting a complement. So this is nothing but A bar dot B plus A dot B bar, the whole bar, because this is XOR and XNOR is the complement of this XOR. So therefore, one way to do this is to use the De Morgan's theorem. Complement of a plus would be the dot of individual complements. Right? So now you can again apply the De Morgan's theorem to each of these individual brackets. So here you will now get A bar bar plus B bar dot A bar plus B bar bar. So bar bar means the same as the old quantity. So if you just open the bracket, you will get A dot A bar plus A bar dot B bar plus A dot B plus B dot B bar. So this will become 0, this will become 0. So what you get is this A bar dot B bar plus A dot B. This is the simplified expression for the XNOR operation. You can also prove this using truth tables. Let's do that for the XOR case. So we said that this is A, this is B. Let's take the A bar column, the B bar column. Let's have one more column for A bar dot B, another column for A dot B bar, and the final column for A bar dot B plus A dot B bar. So A bar will be 1 1 0 0, B bar will be 1 0 1 0. So A bar dot B will now be 0 1 0 0, and A dot B bar will be these two 0 0 1 0. So we need to OR these two to get this, which is now 0 1 1 0, which is exactly the same which we had derived for the XOR in the previous page, which is this. So you may question what is the need of defining these gates like XOR and XNOR and adding to the confusion. While I mentioned that XOR and XNOR are neither universal gates nor are they basic gates, still they have some pretty interesting properties which we shall see not now but a few classes later on, when we are more versed with some of the concepts of the course. We shall see this in more detail at that time. Well, having said all this, let us now ask ourselves a very basic question. You must have seen that in these 3 lectures so far which we have been having, we have written a few truth tables But whenever we have these truth tables, let us say we have two inputs A and B. You must have noticed that while I am depicting the truth tables, I write the values or the inputs in a particular manner. I write for 0, 0, I write 0, 1, 1, 0, and 1, 1. Now there's a reason why I write this way. Well, nothing stops you from writing them in any order. Of course, since A and B each can take only two possible values, 0 and 1, you will still end up with 4 possible rows of this table, so to speak. So the question is, why does the order matter? Well, the order matters because this order is, in a very subtle sense, trying to convey something to you. If you notice something, these are zeros and ones, and we can treat them as binary digits. So therefore, let me call this as row 1, row 2, row 3, and row 4. So if I treat each row as a 2-digit binary number, then what I will see is that essentially these are conveying to me the numbers in order. This 0, 0 is actually the number 0. This 0, 1 is actually the number 1. 1, 0 is actually the number 2. And 1, 1 is actually the number 3. This is in decimal system. Decimal system is that number system which we are used to working with since our childhood. This is the number system with which we are standardized, with which we follow. Here for decimal, the base is 10. That means the base digits are from 0, 1, 2 all the way till 9. Base digits are those digits using which you can make any possible number in this number system. So all the number systems, whether they are natural numbers, whole numbers, integers, even fractional numbers, they are all made using these digits. So therefore they are called as the base digits. In one of the earlier lectures, I mentioned that binary number system is something that we are going to be relying on, because that is how we represent sets of voltages by means of zeros and ones, that is high voltages or low voltages. So in binary system, the base is 2. The base is 2 and the base digits are 0 and 1. This way you can define any number system with any base. So I can say base n number system. In that case, the base digits will be 0, 1 all the way till n minus 1. In particular, there are some number systems or some values of n which are of some interest. n is 2 is a binary number system. n equal to 8 is called the octal number system. n equal to 10 is the decimal number system, and n equal to 16 is a hexadecimal number system. Octal was very popular once upon a time, but now it's not very popular. The most popular ones are binary, decimal, and hexadecimal. because hexadecimal is essentially a more elaborate version of a binary system, which is extensively used in microprocessors and microcomputing systems. We shall look at this in a little bit more detail. The use of the hexadecimal number system, although not from the purview of microprocessors, but we shall definitely see how to use them. So, in this particular lecture, we saw why universal gates are called universal gates. Then we followed that up with some of the basic Boolean algebra theorems and properties. Thereafter, we looked at XOR gates and XNOR gates. And then we started or just broached the discussion on number systems. And we are going to be focusing a lot on the binary number system, which we shall continue in our discussion in the next lecture. Thank you.